Hey everyone, Zach here. I wanted to show off a project I've been working on for a while to make Vulkan a little bit easier to use for personal projects. I learned about Vulkan in my CS 419 class, which is a special topics class. It was only taught, I think, every 4 years. It's not taught every year, it's not part of the main curriculum. It's an elective, and it's a pretty rare elective, and I got the lucky chance to actually take it, and I really enjoyed it. Vulkan was a lot of fun because I got to see all the nitty-gritty, under-the-hood details of what goes into creating a render pipeline versus OpenGL. We used a lot of the stock pipeline when we were doing the OpenGL class, and eventually we did end up using a little bit more of a custom pipeline, but a lot of this stuff was hidden from us, and Vulkan exposes a lot of things that you can tweak to increase performance or specifically tune the features that you need. And I thought that was really cool, but the framework projects that we were given were very, very long. There was like 20 functions or so to set up just the basic pipeline before you could even render things to the screen. And I understand that's necessary, but it was very cumbersome the way we were presented with just a bunch of functions in a file. And I wanted to see if I could improve on that by making it a little bit more modular and breaking it out into individual classes with classes owning specific parts of the pipeline. And this is what I came up with. And this is the main file for the demonstration project. And if we look at it, it's not very long and it's pretty sparse. 128 lines all said with some big comment blocks and a boatload of includes. It doesn't take much to use this framework I've worked up, and that's really cool and I like that a lot. But it still allows for flexibility, having, different pipelines for different shader stages and things like that, multiple objects. I'm pretty happy with it. So I'll go ahead and walk through the code before I launch the demo. And it starts with this VK render agent initializing. And I had originally planned to work on this in the sense of a game engine. I wanted this to be the foundations of the rendering layer of a game engine. Being game programmer, game engines are what I want to work on. So I had this idea that I would set it up in a way that I could use different graphics APIs in a kind of transparent manner. So I have this render agent concept, and you can see I've actually got an iRender agent class, which is supposed to be an interface. I really like the way you can use classes as interfaces. I use that a lot in Unreal Engine for C++, and it works out pretty smooth, so I transferred that over to this. And I've got this idea of having different render agents be capable of using different graphics APIs. In this case, I only have Vulkan implemented, but I intended to create render agents for Direct3D and OpenGL and whatever else there may be. So it starts pretty simple. This render agent takes in 3 parameters: the name of the project, or the title of the window. You'll see when I launch it that this actually shows up on the title of the window, and then an X and a Y. And this actually controls the window size. So if you're going to do full screen, I don't actually have support for full screen right now, but it might be a different initializer and a different parameter, this would set the window size. I've got this shader pack. This is a custom library I wrote to make handling shaders easier. It allows all the stages of a pipeline to be packaged into one file and also extract layout information from it so that it's easier to actually bind and set layout data in the pipeline. This makes it super easy to do things like set uniform variables in your shaders. This shader pack integrates into these descriptor sets, and now these descriptor set classes have a method called set uniform, which makes setting things that change fairly constantly on an object super easy. This is actually deserializing this shader pack file, so it's taking the shader information out of this kind of raw file format. It holds all of the raw compiled shader info, so the SPV shaders get packed into this, as well as the layout data that the render agent needs to produce the descriptor sets. So then I have these two descriptor sets. There's two objects that'll be rendered in this scene. One descriptor set for each object, so I can change things like position and color and whatnot. And the render agent is in charge of producing these descriptor sets. So this again would be in charge of producing the same descriptor set object from different render agents, although I haven't quite got that far. You can see it's using the same shader pack. These use the same descriptor sets. I just want to be able to tweak some values to change color and stuff like that. And then from there, I create the pipeline. That's it. 1, 2, 3, 4, 5, 6 lines to create a pipeline versus 20 functions or something like that. This pipeline is pretty simple. It takes in a target descriptor set as well as a shader pack, and then of course the render agent is responsible for producing the pipeline for which it knows how. So again, a Vulkan render agent would produce a Vulkan pipeline, and a Direct 3D render agent would produce a Direct 3D pipeline. This is some custom code that I wrote to handle object files. So these are 3D format OBJ files that hold the actual model information, and then I'm storing them into a mesh. And then the render agent produces a buffer for the particular graphics API that will hold the mesh data for the object. So I've got a save station buffer and a capsule buffer, and this mesh is just kind of an intermediate thing to load into, and then it loads into the actual buffer. And then I actually create these objects. So VK renderable implements iRenderable. So this is kind of the base renderable object target interface. Every graphics API would implement iRenderable to have something that it can draw, and then the render agent renders it with the render call. You can see it takes in an iRenderable, and then it will render depending on what particular kind of pipeline it is. So I've got two different kinds of objects here. I've got a VK renderable, which is just kind of the base Vulkan object that I have, and then I have a VK rotating object which implements VK renderable or extends VK renderable. This VK renderable is just kind of a stationary object. You can move it. However, this VK rotating object takes this saved or this VK renderable and implements a rotation on it every time update is called. So when I launch the project, you'll see one object is stationary and the other is rotating, and the rotation happens automatically when I call update on the object versus having to manually set the rotation. This was a cool example of how polymorphism can really add some powerful features to games. So I was playing around with this idea. This was helping me learn a little bit more about polymorphism with things like Unreal Engine, because you can do a lot of the same stuff with actor classes and object classes in Unreal Engine. And then I have some time setup stuff. This isn't really a very good time system for an industrial strength game engine. You'd want to do some things to try and smooth out the time between frames versus just taking the time and spitting it out. For this demo, it doesn't really matter. If it stutters, it stutters. Nobody will really notice it, and if they do notice it, at least for a demonstration, nobody's really going to care. I'm not trying to do a 60 frames per second fast-paced action shooter where, something being off could potentially impact the game. This is just a demonstration, so this works fine. I do some setup on the objects now. So these also have an init function which does some extra setup. The save station actually, the VK renderable init doesn't really do anything. It does all of its initialization in its constructor, but the capsule init does some setup. This VK rotating object does do a little bit of initialization. And then here I'm setting the world location and the rotation for the save station. I'm setting the scale on the capsule here. And then here's where I'm actually changing the color of the capsule. And you can see this is working on the descriptor set, not the object. And I'm calling this set uniform. And this set uniform is a custom function that I wrote that allows you to map the descriptor's name in the shader to its place in the buffer. And this is a really cool way to make it as easy as just saying, hey, I want to set this descriptor or this uniform with this name to this value. And it works really easily. So I'm setting this uniform called color buff to this color, telling it how big it is and what the offset is. So name of the uniform, value, the size of the value, and the offset. Because this is a pointer, it's a void star, so it takes whatever this is and just puts it in raw data. So if you do use this project, be aware of that if you've got some weird things that you're trying to shove into your shader, it might throw up. And then I'm calling the render. So what this does is this actually submits the render job to the pipeline, and then finally display actually submits the queue. So what this is doing is this is putting the object in the queue. These both are putting, one puts the save station and the other puts the capsule into the render queue, and then display actually dispatches the queue to the hardware to be rendered. And then I've got a really basic game loop. Since I'm using GLFW, under the hood this render agent knows how to ask GLFW if the window should close. So I've got this function window should close. It just returns a Boolean value, true or false. So while that window should not close, we do this update cycle. This GLFW pull events is really important here because otherwise the window will lock up. Windows thinks that it's in a infinite loop and it's locked up. So if you try to move the window around or actually click close, nothing will happen. Doing this GLFW pull events keeps that from happening. So GLFW handles the Windows events. In a real game, I'd probably actually do all the Windows interfacing manually. So I'd have a Windows event pump going on to handle that. More time code. This actually gets the delta time from the start of the render to now. I could change this around. It doesn't really matter. Basically, it's getting you the time between the last update. So you know that if you want to smooth something out, you can apply the delta time to that. And that's what this is doing. So the save station update is applying the delta, and the capsule update is applying the delta. And this is what actually causes the capsule to rotate, which you'll see in a second. And then again, I'm calling render on the objects that I want to render, and then display. So go ahead and start this up. And there we go. So you can see I've got two objects, the stationary save station, and if you've seen my final project in my portfolio for my OpenGL class, this will probably look familiar. This was modeled after the save station from Metroid Prime. And then I've got this little kind of capsule thingy with a forward direction indicator on it spinning around. So you can see the save station update doesn't really do anything, it just kind of sits there. And this capsule update causes it to rotate. And then of course the name of the window shows up here, so Vulkan demo, and it's 800 by 800 pixels. So that's really about it. I won't go into all the detail about what goes on under the hood of the render agent. It's pretty simple. I just have everything split up, so I have a class to handle the device instance, the Vulkan instance. I have a class to handle the physical and logical device. I've got a class to handle the view. And then, of course, I've got classes for the descriptor sets and pipeline and buffers. And they all just kind of fit together like puzzle pieces in a way that you could override them and implement new features if you wanted to, or just simply add a new initializer or new code to do different things. The only thing that I really want to change on this right now is that a lot of the details are kind of hard coded, so doing some of the tweaking to the pipeline is is not as simple as just changing a value in the initializer. You actually have to go into the definition of the class and change things manually. But I haven't quite figured out a good way to do that without making it really cumbersome. So for now, this works fine, and I'm pretty happy with it. So that's it. You can find the code on my GitHub repo. I will post the link in the description. And if you check out my website, you can also click on the GitHub tab, and that will take you to my GitHub repo, which is where this will be. Thank you for watching. I hope you've enjoyed. And if you need Vulkan for a Windows C++ project, this might work pretty well for you. Catch you next time.